Hi everybody, we are Group 4 and in this video we'll walk you through how we built and tested our UAV in Unity, starting from our original CAD model, built in Fusion 360. Now, before we import the CAD model into Unity, we make sure that the model reference point is set correctly. That reference location that I'm referring to is at the wing's leading edge, just along the green line here. And Unity uses it for position, rotation and force calculations. Getting this right early makes the simulation much more reliable. The model is then exported for use in Unity by clicking on the top left, export, and selecting either a .fbx file or a .obj file. Now we opted for a .fbx file because it was a file format that preserves the orientation and the part structure, which makes the alignment and the setup far smoother once the model is in the simulation environment. FBX keeps the transforms, part structure and rotations, which is ideal for Unity, and the OBJ file is just a static mesh and often needs manual fixes, so in this case we opted for the .fbx file, and to do that we click export and then we just go to Unity. Next, to import the FBX file into Unity, you drag this FBX file into the assets folder here, and once that's complete you drag the aircraft FBX file into the scene. You're checking three things: that the scale is correct, the rotation matches the simulation aircraft provided by the Excel sheet, and lastly that the geometry is imported cleanly without any errors. The CAD model here is used as a visual reference only, and the physics and the aerodynamics are handled by the simulation aircraft provided in our Excel sheet. This now concludes the import into Unity. So once the geometry is aligned, we set up how the aircraft behaves physically. Colliders have been added to represent where the aircraft has mass and volume, such as the fuselage, the wings, the tailplane and the fin, as you can see here. These colliders are what helps Unity understand how the aircraft moves and reacts to forces, and then we add aerodynamic objects to the main surfaces to tell the simulation where the lift and drag is produced during the flight. Next, the control surfaces are adjusted to match the CAD model. The elevator, the ailerons, the rudder has been repositioned so the hinge line and rotation axes align correctly. The deflection limits of the control surfaces have been updated into the aircraft definition at the top here. We can see that the ailerons have a max up and down deflection of 10 degrees, same with the elevator, we're not using flaps, so it's 0, and then lastly the rudder, max deflection of 30 degrees. Before testing, we need to verify the total aircraft mass, which we can see at the top here, 4.9 kilograms. And then the centre of mass location is 0.154 meters after the leading edge and 0.1 meters down. This step is critical as both the mass and the centre of gravity have a huge influence on stability and trim. This moves us on to the next part, which is wind tunnel testing. To locate my aircraft in the wind tunnel, I need to click on Aircraft Simulation, Tools, Locate Aircraft in Wind Tunnel. This now positions the aircraft inside the wind tunnel, and as long as my two boxes here are ticked where it says moving part and uniform flow, I can change the wind speed by adjusting the slider and change the direction of the airflow by changing the azimuth angle here. So by checking that the aircraft behaves sensibly in the wind tunnel, you can reduce your chance of losing the aircraft during its real first flight. It acts as a confidence check before moving on to free flight testing, and it helps justify our design choices. We can actually adjust the speed of the wind, we can adjust the azimuth, which is like the heading angle of the wind, we can adjust the elevation of the aircraft, and also we can record data. The data can be recorded by clicking on DAQ tab in the hierarchy, moving over to the right to open the plot window, and then choosing some variables that we'd like to measure. For further analysis in our reports, and we can export all this data into text files by clicking Export All Data, and it will save that in the Assets folder again for you to analyse and download. So finally we move into free flight. During the stage, the heads-up display gives us the live feedback on the aircraft. We can see this key information on the top right, which makes it easy to check trim, stability and confirm that the aircraft is operating safely throughout the flight. During these tests, the aircraft successfully achieved a takeoff distance of 10 meters, meeting one of our key design requirements. This final stage ties the whole process together. Thanks for watching.